Good day. Study Unit 6 focus on multiple regression in Chapter 14, which is on page 331 in your textbook. In SCTN 111, you looked at simple linear regression where you fitted a straight line through your data and you only looked at one independent variable which was indicated by X. But now in multiple regression, we look at more than one independent variable at a time. So we will fit a plane through our data, like indicated in this diagram. There's very few calculations in this chapter since we do multiple regression on a computer program. So the output will be given to you in a test or exam, and you should be able to interpret the output then and obtain the values from there. So the program that we are going to use in the textbook to obtain the computer output is STAT 1.3. If you look at the outcomes in the study guide for part 1, you need to understand what is meant by multiple regression versus simple linear regression that you did in chapter 6. So I'll quickly recap on the important concepts that you did in chapter 6. Then you need to be able to determine and interpret the regression coefficients from your computer output. Then you should be able to predict the dependent variable, which will be indicated by Y, when the values of the independent variables, and that will be your X variables, are given. Then you should be able to understand what interpolation and extrapolation means for multiple regression, and then you also need to interpret your coefficient of determination indicated by R squared and the adjusted coefficient of determination indicated by RA squared, and you will locate those values from your computer output. Chapter 14 is the extension of chapter 6. Let's quickly recap on a few concepts in chapter 6. So in chapter 6, you want to determine whether there was a linear relationship between your independent variable X and your dependent variable Y. So a linear relationship means that you can fit a straight line through the data. Let's say, for example, that we define Y as the marks obtained in a test and X as the hours studied for the test. Then we can graphically represent the data with a scatter plot to see whether there is a linear relationship in our data or not. Then we can also measure the strength of the linear relationship with the correlation coefficient indicated by R, and this is always a value between -1 and 1. If that value is positive, then it means that there's a positive linear relationship between X and Y. And if that value is negative, it means that there's a negative linear relationship between X and Y. The closer the value is to -1 or +1, the stronger the linear relationship will be. And the closer the value is to 0, the weaker the linear relationship will be between X and Y. Then you determine the linear regression equation in this form, and if you substituted values for X, you could predict the value of Y. You can also calculate the coefficient of determination, which is indicated by R squared, and this tells us how well the regression line fits the data, since it represents the percentage of variation explained in your dependent variable Y by the regression model based on your independent variable X. But perhaps the hours studied is not the only variable or factor that influenced the test mark, as we indicated that by Y. For example, other factors or variables that can also influence the test mark is the IQ of the student and the motivation of the student. So we can define 3 independent variables now. X1 represents the hours studied, X2 represents IQ, and X3 represents motivation. So we can expand our simple linear regression model into a multiple regression model indicated by this regression equation. So Y hat will be your predicted value of the test mark if you substitute different values for X1, X2, and X3. where x1, x2, and x3 is your independent variables. B0 indicates your y-intercept, and B1, B2, and B3 will be your regression coefficients for the independent variables. In general, if we have, for example, k independent variables, then the theoretical regression equation will be given by this equation. So beta 0 indicates your y-intercept, and beta 1, beta 2 up to beta k will be the unknown regression coefficients. And then epsilon will be the error term. So that will be the unexplained variation if the regression model doesn't fit the data perfectly. So that's your residuals, the difference between your actual value for your independent variable y and the predicted value of your independent variable y. And then x1 up to xk represent your independent variables. Since we can't always observe the whole population, we can use sample data to estimate our multiple regression equation to make predictions. So your estimated multiple regression equation will be given by this equation, where y hat is the predicted value of your dependent variable. B0 is the estimated value for the y-intercept, and B1 up to bk will be the estimated values of your regression coefficients. Since the calculations are complex, we use a statistical computer package, and there's quite a variety of them to estimate these values. So you should only be able to interpret the computer output for stat 1.3 that we will use to determine these values. The background to the chapter example is given on page 332. So there they tell you, the marketing division of a manufacturer of electronic games wants to know what the effect of different types of advertising is on the sales of their product. So they define the dependent variable y as sales, and the data is in millions of rand, and the two independent variables is as follows. X1 is the radio and TV advertisement expenses, and that's given in thousands of rand, and X2 is the newspaper advertisement expenses, and that's also given in thousands of rand. So in table 14.1 on the next page they give you the data input. The data was recorded for 22 cities, so our sample size is 22, and just take note that the sales was input as decimals to make the data processing and input easier, but remember sales was given in millions, so for the first city the sales of 9.73 will represent 9,730,000. The same for the radio and TV advertisements, and those were recorded as thousands of rand. So the 5 in city 3 will actually represent 5,000 rand for radio and TV advertisements, and the 5 for newspaper advertisements in city 3 will represent 5,000 rand. Since we have two independent variables, we can write our multiple regression equation then in this form. Since we have two independent variables, our graphical representation of the data will be a three-dimensional scatter plot. And don't worry, you don't have to be able to draw this in a test or exam. And since we are working with multiple regression equation, we will fit a flat plane instead of a straight line through the data points. But the concept of least squares still applies here. So the computer will minimize residuals to obtain the best multiple regression equation. That means that the distances between the actual observations and the flat plane that is fitted will be minimized. I also included the two-dimensional scatter plot for each independent variable against the sales each time, so that you can get a clearer picture of the linear relationship between that specific independent variable and the dependent variable. So if you look at X1, which is radio and TV advertisements, against Y, the sales, you will see that there's a positive linear relationship between sales and radio and TV advertisements. There's also a positive linear relationship between the newspaper advertisements X2 and sales, but the linear relationship between X1 and Y seems stronger because the data points were more concentrated around a straight line, so there were less variation in your data. I highlighted the different sections of the computer output that you should be able to interpret in this module, and we will look at each section in detail, but I just want to point out some important things on the first section of the computer output. So if you look at the multiple regression output, first of all, they show you what your dependent variable was and what the independent variables were. Then the number of observations of 22, that will be your sample size, and they also give you the means of the variables in the next section. So here you can see how the data was recorded. It was recorded as decimal values because the means of the variables were given as decimals. Then in your correlation matrix, you will find the correlation coefficient of all the variables. And it doesn't matter if you read it off in the column or the rows, it gives you the same values as it's just the matrix. So between Y and X1, your correlation coefficient was 0.791, and between Y and X2, the correlation coefficient was 0.594. So here you can see that confirms our graphical representation, because there will be a stronger linear relationship between Y and X1. First of all, you need to be able to determine the multiple regression equation. So you will look under the section on your output that says regression coefficients. And then we look at this column, B parameter estimates, to obtain the estimated values of the regression coefficient. So the value that is next to the intercept, that will be your B0. This value that is next to X1 will be your B1, and this value next to X2 will be your B2. So we can write our multiple regression equation as this. Just remember that you take the sign with, so if any of these values were negative, you would put a minus in your multiple regression equation. You should also be able to interpret the values of the y-intercept and your regression coefficients in the context of the problem. But before we look at the chapter example, let's just look at these values in general. So for your y-intercept, that gives you the value of your dependent variable if your independent variables are equal to 0. And then for your regression coefficients, if the regression coefficient is positive, then your dependent variable will increase by b units if that independent variable increases by 1 unit, while the other independent variables stay constant. But if your regression coefficient is negative, then your dependent variable will decrease by b units when your independent variable increases by 1 unit, while the other independent variables stay constant. Our B0 is equal to 5.257, so that means that our sales will be 5,257,000, since it was measured in millions, if there's no expenses on radio and TV advertisements and no expenses on newspaper advertisements. Then B1 is equal to 0.162. So since that value is positive, it means that our sales will increase by 0.162, or 162,000 in millions if radio and TV advertisements expenses is increased by 1 unit, which was measured in thousands of rands, while newspaper expenses stay constant. And then B2 is equal to 0.249. So that means that our sales will increase by 0.249 or 249,000 in millions if newspaper expenses increase by 1 unit, which was also measured in thousands of rand, while radio and TV expenses stayed constant. We can also use the regression equation to make predictions. So they ask you on page 335 to predict the sales if radio and TV expenses is 8,000 rand and newspaper expenses is 8,000 rand as well. Okay, remember our X values was given in thousands of rands, but we recorded the data as decimal values. So when you substitute your data now for this example, you need to substitute it as decimals. So 8,000 will be 8 for x1, and x2 will also have a value of 8. So if you plug that into your equation, you will get y hat as 8.545. Okay, but remember, our original units for sales was millions of rands. So if you multiply that amount by 1 million, you will get 8,545,000 rand for the predicted sales. With predictions, we must distinguish between interpolation and extrapolation. For multiple regression, interpolation is the calculation of the y value within the region of the observed x values. But if the values that we substitute are outside of the region of observed x values, then we call that extrapolation. So extrapolation is more risky, so it should be handled with care, because predictions made from values that fall outside of the observed region can lead to nonsensical answers. You can try exercises 2A and 2C at the end of chapter 14 to practice the concepts in this first part of chapter 14, please. The coefficient of determination is denoted by R square, and this is a measure of how well the least squares curve fit the observed data, since it gives the proportion of the variation in y that is explained by the regression equation or the regression model. And this is based on the independent variables that are included in the model. Now your total variation in y, which is denoted by SSTO, that stands for the total sum of squares, consists of two parts, the SSR and the SSE. The SSR is our regression sum of squares, and this is the explained variation in y. Since this variation is the part of the regression equation that explains y based on the x's, and SSE is your unexplained variation in y, and it stands for error sum of squares. So this is the variation that is not explained in y, since it is other variables or factors that will also have an influence on y, but it's not included in the regression model. Now the computer computes the coefficient of determination by looking at the proportion of explained variation over the total variation, or you can say 1 minus the proportion of unexplained variation. Your SSTO can graphically be seen as the difference between the actual observations and your mean value for y, and then SSE is the difference between your observations and your predictions that you make, so your regression line. And then the SSR is the difference between the regression model and your mean. What is important is that you can read off this value from your computer output. So under model fitting statistics, you will see there's a R-squared value and adjusted R-squared value. So your R-squared here of 0.9277 is your coefficient of determination. So if we have to explain that in terms of the chapter example, then we can say that about 92.77% of the variation in the sales is explained by the independent variables in the regression equation. That means your X1, which indicated the radio and TV advertisement expenses, and X2, which denoted the newspaper advertisement expenses. The multiple regression equation was then a very good fit to the observed data. But what about the other 7.23%? That will be due to other factors. So examples include the location of the business, and since electronic games can be seen as a luxury item, it can also be related to economic conditions, which will also have an impact on sales or the price of the product, the demand of the product, etc. So all those variables can also have an influence on your sales. You can try exercise 2B at the end of chapter 14, please. One of the values that you should be able to calculate is the adjusted coefficient of determination, and this is denoted by RA square. It is given on your computer output, but sometimes we block it out and you have to calculate that value. Now we use the adjusted coefficient of determination if we want to compare studies with a differing number of independent variables. So to see if an independent variable should be included in the regression model or not, we can use the adjusted coefficient of determination for this purpose and not the coefficient of determination, because when another x variable is added to the regression model, then your coefficient of determination will always increase. But you can't have an infinite number of x variables in your regression model. So the adjusted coefficient of determination takes the number of x variables into consideration, and it indicates if it really is better that we add another independent variable or not, because it can decrease if there's not a significant reduction in the SSE. Now, if we go back to our textbook example, if we only include the radio and TV advertisement expenses, then your adjusted R-square value will be 0.6069. But if I add the newspaper expenses as well, so we expand that simple linear regression model into a multiple regression model with two independent variables, then our adjusted coefficient of determination will be 0.9201. So that means that we should include newspaper advertisement expenditure as well, since the regression model will be better and more variation in sales will be explained as a result of that. If I do not give you the value of the adjusted coefficient of determination on the computer output, and I ask you to calculate that, you can use this formula for that purpose. N represents the sample size, and K is the number of independent variables, and then R square is the value of the coefficient of determination. Now, if we go back to our chapter example, our N was 22 since we observed the sales in 22 cities, and K was 2 since we looked at radio and TV advertisement expenses and newspaper ad expenses. And then the value of our coefficient of determination was 0.9277 as we saw on one of the previous slides. So if you substitute that and you calculate your adjusted coefficient of determinations value, it will be 0.9201, and this corresponds to the value that was given on your computer output. You can then calculate the adjusted coefficient of determinations value for exercise 2, please. We had a sample size of 10, so n will be equal to 10, and there's 2 independent variables, so k will be equal to 2. And then we already looked up our coefficient of determination on the previous slide, so your adjusted coefficient of determination will be 0.8763.